Hello Physics Nation, my name is Nate Larmond and I'd like to do a problem from Giancoli, Chapter 8, number 5. An ice skater is in a spin with his arms outstretched. If he pulls in his arms, what happens to his rotational kinetic energy? This is actually a classic trick question. This is often replaced with rotational momentum or angular momentum. So here's my diagram. It's classic demonstration. We're going to spin with our arms out. The y-axis is coming out at us, so we would say we have an angular momentum about the y-axis, and we pull our arms in. What that does is it changes the moment of inertia. So for the sake of this problem, let's assume the final moment of inertia is half of the initial moment of inertia. Let's also assume there is no external torque applied, so that angular momentum is conserved, that is constant. Alright, so the product of the moment of inertia and the angular velocity is the angular momentum. We're going to set the initial angular momentum equal to the final angular momentum, and all we do is we substitute in our assumption up here. So the final moment of inertia is half of the initial moment of inertia. We divide both sides by that term and it disappears. We multiply both sides by 2 and we get the final angular velocity is double the initial angular velocity. So not rocket science. You observed the spinning increase when the person pulled in their arms, and this is just the sort of algebraic version of what you observed with your eyes. Now let's observe what happens to the kinetic energy. So the momentum remained a constant. The angular velocity increased by a factor of 2 if we cut the moment of inertia by a factor of 2. So we're going to do the same trick, except we're going to do 1/2 mv squared, or in rotational version, 1/2 I omega squared. Here's our first assumption, that the final moment of inertia is half of the initial moment of inertia. So there's our first substitution. Here's what we just figured out. That means a twofold increase in the rate of angular spinning. That is the angular velocity right here. So you square both terms, obviously, and that increases the kinetic energy by a factor of 4. However, the moment of inertia dropped by a factor of 2. So this factor got cut in half, and this one was increased by a factor of 4. So if we compare those two changes with this ratio right here, final kinetic energy divided by initial kinetic energy, it turns out to be a change of 2. That is, the final kinetic energy is double the initial kinetic energy, which is kind of tricky because, there's no external torque, so we don't have a change in momentum, but work is actually done. It's done in the radial direction. You actually feel your muscles contracting when you pull your arms in. That's where the extra energy comes from. So here's the written version. The skater applies an inward radial force, and therefore does positive work. The force and the displacement are in the same direction, causing an increase in kinetic energy. Thanks for watching. See you in the next video.